In this video, I'll talk about elementary reactions versus complex reaction mechanisms. So first, let me give you one example of elementary reactions over here. So in this reaction, we see the coefficients in front of H and HCl is 1 here and 1. So that means one hydrogen atom collides with one HCl and forms H2 plus chlorine. In an elementary reaction, the reactant coefficients are very important. These numbers, these coefficients, tell us the order of the reaction. So we see this is 1 here and 1 here. That means this reaction is first order with respect to hydrogen, and also first order with respect to HCl. So again, these elementary reactions describe the actual collisions between the actual numbers of reactants as the chemical equation indicate. If you see 1H here and 1HCl here, in the real reaction, you have 1H atom attacks 1HCl molecule. In general, the elementary reaction A plus B to form products indicates that indeed there's 1A collides with 1B to form the products, and the reaction rate is simply K times A times B. This is a second order reaction. It's first order with respect to A and also first order with respect to B. How do we know this? If it's an elementary reaction, we just need to look at the coefficients in front of A and B. It's just 1 and 1. All right, so sometimes we see 2 A's to form product, or A plus A. So in this case, if this is an elementary reaction, we know that 2 A molecules collide with each other to form the products, and the reaction rate is simply K times A to the power of 2. Where does this 2 come from? This 2 is the coefficient in front of this A. So these two examples, A plus B and A plus A, or 2A, these examples are bimolecular reactions. So in these examples, we have two molecules collide with each other. In this case, A collide with B. In this case, A collide with A. All right, those are bimolecular reactions. So there are also uni molecular reactions. In this case, we have a coefficient here, just 1A. This 1A becomes the products. So in this case, the reaction rate is simply K times A to the power 1. This is a first order reaction. All right. Sometimes we see A plus B plus C, or 2A plus B, or 3A react and form the products. So what's in common? They're all third molecular reactions. I'm going to assume these three reactions are all elementary reactions, and then it tells us in this example you have three particles, A, B, and C, collide at the same position simultaneously. If the orientation is right, if they have enough energy to overcome the barrier, products will be formed. In this case also, three molecules will have to collide with each other, 2 A's and 1 B. In this situation, 3 A particles or 3 A molecules will have to bump into each other at the same time, at the same position to form the product. Again, you have to have the right orientation for the collision, and these three molecules will have to have enough energy to overcome the reaction barrier. So what's the reaction rate? For the first example, A plus B plus C, you see the coefficients in front of A, B, C are 1, 1, 1. Therefore, the reaction rate is K times A times B times C. For the second reaction, if you look at the coefficient in front of A, that's 2. Therefore, this reaction rate is K times A to the power of 2 times B. And then the last example, the reactants are 3 A's. Therefore, the reaction rate is K times A to the power of 3. Again, we're talking about elementary reaction here. Third molecular reactions are rare. Why? Just imagine the chance of seeing three blindfolded flies, just imagine they fly around, and they bump into each other in air simultaneously. All three flies bump into each other in air. The chance is very little. Okay, so now reaction mechanisms or complex reaction mechanisms. So I probably should put complex here just to emphasize this is a complex mechanism. It consists of a series of elementary reactions. For example, if you look at this reaction, it looks simple. Two hydrogen molecules react with one oxygen molecule to form two water molecules. It's not an elementary reaction. So this coefficients, this 2 and this number 1 in front of oxygen do not tell us the reaction order. And we cannot simply say it's a third molecular reaction. So what's going on in this reaction mechanism? Well, there are many steps. All right, so first initiation, we have decomposition of H2, we have decomposition of O2. And then we have branching reactions. We have H reacts with O2, we have O reacts with H2. And we get OH radicals, and OH can attack this H2 molecule to form water, and this H atom will again react with O2 to form this hydroxyl radical and oxygen atom. So this goes on and on until all H2 and O2 are consumed and water is produced. For such a complex mechanism, the coefficients, again this 2 and the 1 in front of O2, tells nothing about the order of the reaction. This reaction is not a second order reaction with respect to H2. It's not a first order with respect to O2. And it's not overall a third order reaction. We just don't know anything about the reaction rate of this mechanism. So finally, I have a question for you. How do we know if a chemical reaction is an elementary reaction or a complex mechanism? Well, again, a complex mechanism consists of multiple elementary steps or elementary reactions. So sometimes we say elementary steps, sometimes we say elementary reactions. So how do we know? So for example, if I give you another reaction, like this, how do we know if it's an elementary reaction? The coefficients in front of the reactants are the orders, the corresponding reaction orders, or it's a mechanism in which the coefficients do not mean anything. So how do we know? The answer is simple. We don't know. We just do not know. We have to do quantum mechanical calculations to confirm, to make conjectures. But here's something we do know. If you have a chemical reaction, you look at the coefficients in front of the reactants. If the sum of the reactants' coefficients is 3 or more than 3, then this reaction is more likely a complex mechanism instead of an elementary reaction. Why is that? It's very rare to have third molecular reactions.